Welcome back after the break and the workshops. I hope you had fun playing games in your workshops. I heard that it was quite a lot of fun. We come to our third session, and for excellent projects we want to present. And they all deal with water. Yeah, water, the basis of our existence. Recently I did a talk about the situation of the rivers and creeks in Germany, and it's really sad, but to say that they are in really bad condition. That's a result of a join-in campaign of ARD, of the television, public television station Unsere Flüsse, together with Helmholtz Environmental Research Center. 3 out of 4 streams surveyed do not provide a good habitat for fish or insects. And according to the EU Water Framework Directive, all watercourses should be healthy and alive by 2027. Experts believe this goal is almost impossible. But wastewater management, for example, plays an important role, and therefore we are really curious to listen to the next session about projects that are dealing with digital solutions for sustainable wastewater and water management. So please welcome our chair for this session, Professor Dr. Katharina Teuber. She's professor in the field of urban water management at Jade University of Applied Sciences in Wilhelmshaven, Oldenburg. So welcome, Katharina Teuber. I would like to introduce you. You completed your doctorate at the Technical University Berlin as part of the DFG Research Training Group Urban Water Interfaces in the field of water management and hydro systems modeling in 2019. Then you worked as a project manager in the Research and Development Department of Berliner Wasserbetriebe in January 2022. You were appointed professor in the field of urban water management at Jade University of Applied Sciences, and in June 2023 you were elected to the board of the Institute for Pipeline Construction in Oldenburg, and that's also good to know because you have also practical experiences. So we are really curious to listen to your talk about digital water management challenges and chances. And afterwards, you present the projects, and we have time to ask questions and discuss what you were telling us. So the stage is yours.
Thank you very much. Thank you for the kind introduction. Thank you also very much for the invitation to this conference. So I'm going to give you a short keynote presentation, and afterwards we are going into the Digital GreenTech projects. So the title that I chose was Digital Urban Water Management Chances and Challenges, and let's see what this contains. So first of all, probably you have seen it in early 2024, this year, we saw a headline in the newspapers that Google developed a new model that was able to predict floods faster than previously developed models. So we see there is new developments arising here. Sorry, what's happening? Sorry, I pressed the wrong button, I think. So we see there are new models being developed. AI is on the rise. And also what we see is that big corporates are going into the field of environmental technology. They are looking at how can we predict floods faster than other tools, than municipalities, for example. And why is this important? Because we need to see that some might think we don't need research anymore in this field because we have big corporates that are developing those models for us. Why don't we trust them and save all the money for research? And at the same time, we know that if we give the power over to those big corporates, it might put us in a bad situation, and maybe at some point they will decide to make it commercial, these tools, and then we cannot access the data anymore, and we don't have these predictions anymore. So this is why we should keep up the research in the field, and this is the motivation. So we also have current challenges. So we all know climate change is a big challenge in our field. We have still increasing urbanization, we have aging infrastructure, and we have stricter legal regulations. For example, the wastewater treatment directive that is currently being discussed. And why do we talk about digital transformation of those urban water systems? So, and what is this? Let's see a short definition. It's often talked about as water 4.0. And it is the transformation of the water industry towards connected systems, towards digital systems. And the idea is to have a stronger customer focus, to have better networking and better, better networking within the value chain. And the goals are to have a better linkage between plant processes, to have better speed, to consider all resources, personnel, material, and support processes, all towards the goal of having better environmental technologies. And there have been some research activities going on to measure these effects and to see how is the state of the digitalization. Oops, sorry. And there are the so-called maturity models which have been developed in 2019. What they found out, I think all of you are able to read this German description. So the idea is there were several steps that could be achieved. First was the simple computerization, and in the end, last stage would be adaptable systems, self-optimizing systems. So what was found, the status quo in 2019, was that the average level of maturity was somewhere between 2.6 and 3.2. So we see where we have this orange line. It's in between connectivity and being able to see the data. So this was 2019, still some years ago, but we see until having self-optimizing systems, there's still a lot of work to do. And then at BWB, back then, I was able to join one project of the first Digital GreenTech call. It was called Blue 2035. We started when did we start? 2021, right? In the middle, and in the middle of 2021, and I was only able to join this project for 6 months because then I went to the Jade University of Applied Sciences and I left the Berliner Wasserbetriebe. But still they continued the project and had some nice results that I wanted to show as an inspiration. So the idea was to have a picture for the future of the digitized water industry, to see where should we go, what are the main steps, what are main theses that should be followed. And they developed this paper containing different fields, different topics that are seen to be relevant for the future. And I brought to you today 3 of those images and wanted to highlight them a little more. So the first one that was most important, I think, is digital transformation of the water industry has begun and can no longer be reversed. So at the same time, there was this phrase saying digitalization not as an end in itself, but a means to the end. So always have the focus, why do we do this? Why do we use these digital tools? And then to more, we have seen this in the workshops, in the game, so AI-based systems. The thesis here is AI-based systems will be used company-wide in the future. and digital twins will accompany the industry. And there, that building information modeling will be a part of the digital plans. So let's have a look at digitalization and wastewater treatment. And I brought two examples of my work where I was working in. So first of all, AI and wastewater treatment systems. So in the research project WindNode, we focused on how can we predict with AI, so machine learning models, ammonium effluent concentration at the wastewater treatment plant. The idea was to use this to have a load management to reduce energy consumption in the biological treatment stage of the wastewater treatment plant, and to be able to have flexible loads and save energy when it's needed somewhere else. And we used these AI tools, we used machine learning, we had some nice predictions, but the research has gone on since then, and a current trend that I wanted to highlight here is we have on the one hand mechanistic models for wastewater treatment processes, so these process-based models, and on the other hand we have machine learning models, and now there is this discussion, how can we join them? How can we maybe create hybrid models to have the best out of both worlds? So on the one hand side, knowledge-intensive models, on the other hand side, data-intensive models, and how can we connect those to get a better outcome, to get better wastewater treatment. And then BIM. So it's always a topic, what about building information modeling? And I went to the Jade University of Applied Sciences. I'm in a faculty of building systems. So I'm working a lot of, with a lot of civil engineers. And all of them, if they talk about digitalization, digital twins, they are talking about BIM models. And for me, often a digital twin has been a process model. So the idea was, how can we connect those two topics? So how can we connect two ideas of the digital twin? Especially if we look at building information modeling in the water industry, it's still somewhere, it hasn't gotten a wide application at the moment. So everyone is trying to implement those systems, but because wastewater utilities, they are focusing a lot on the operation phase. They are sometimes questioning, why should I implement these BIM models if they are focused on the building phase? Because the building phase is just a short amount, and then we have this whole operation phase, and where can I use these models in the operation phase? And there is this white paper by the Building Smart Working Group, and it also highlights, well, the operation phase for water systems is much longer than the planning, the building. And there are some use cases that have been defined. And for me, and you know now what I did before, you see they said energy management, monitoring, simulations, CFD simulations I did in my PhD. So I thought, well, this might be something that's interesting. How can we connect those two things? And I have a very nice colleague, a professor for BIM actually, and we are currently trying to connect those two worlds somehow. To get better outcomes, better digital twins by combining the building model and the process model. And then something about the assessment. So what can we do with these models? What are the chances and the challenges, as I highlighted in the title? So first of all, we have innovative technologies. We also hope that there is a positive environmental impact, that we have better effluent values, that we have energy savings. We also hope that there is a workload reduction. But I put this in brackets because at the same time, we find now that the workload reduction also comes with the need of upskilling. So we need to upskill our personnel, we need to show them how they can use those digital tools, and in the beginning, in the implementation phase, it's sometimes more work than saving work. And also the environmental impact we need to keep in mind. And there are some other strengths: increased efficiency, sustainability, forecasting possibilities that we hope we get from those models. But on the other hand, we have some risk, we have some weaknesses. So first of all, some ethics concerns. We have regulation. The new EU AI Act is something we need to consider, and possible rebound effects. And I brought a few quotes as an end, so to say. And there's one, it goes a little in the direction of the first keynote presentation, saying, maybe you've seen it in the paper Brand 1, the latest version. They have the study published there. The global AI demand might be accountable for 4.2 to 6.6 billion cubic meters of water withdrawal in 2027. So huge amounts of water demanded by those tools that we need to account for if we want to somehow account those positive environmental impacts. And also another more in the ethics direction concern that we need to think about equal chances. So there is a nice study saying that the pressure to reskill this workload in the beginning that we put into the implementation phase might be harder on women, because it's usually something you do during your leisure time, and it might put more pressure on women that are taking care of household responsibilities. And also that if we have, for example, intelligent water management strategies, we also need to consider that they might fall into the direction that they punish people who do care-related activities and put more pressure on them. So this is something we need to account for to see how we can balance those effects out. So summing up, I think we have also in this talk, we have AI for sustainability, but also we need to consider the sustainability of the AI systems. And this is where I want to end. Thank you very much. Okay, and now I would like to go into the project presentation. And first up, we have Dr. Tim Fuhrmann with the project Live Sewer. Thank you very much.
Good afternoon, dear colleagues, and thank you to Ms. Teuber for the short introduction, which I would like to take up to introduce to the project Live Sewer. It's okay. I guess most of you are familiar with this kind of cover of the public sewage system. But also most of you are not aware about the situation below these covers. And especially you are not aware about the specific operational challenges within the sewer network. But not only you, even operators often don't know much about the current operating status of their system. This is also because there are hardly any sensors due to the very difficult installation situations in the sewer network. And there are lots of different discharges that are mostly difficult to monitor continuously. And in addition, we have different biological processes, so problems like odor, corrosion, etc. occur. To tackle these challenges, within the Live Sewer project, we developed the idea to have some kind of automated monitoring system. And we tested the system at sub-catchment areas in the city of Rheine, in the Münsterland, and also in the region of Emscher-Lippe. This is where I come from. For that purpose, sensors have been installed at certain points of the sewer network, where standard parameters, wastewater parameters, measured continuously, and this results. This data is transmitted to cloud-based storage systems, where they are available for intensive data analysis. This data analysis can be used, for example, to trigger specific processes within the sewer network, as there could be sampling or, for example, the dosing of chemicals. Actually, we are working on data analysis for the following applications. First of all, it's we call it a discharge surveillance, which means that through the automatic recognition of patterns of the measurement data at 24/7 monitoring is possible. This can be used on the one hand side for the detection of anomalies, but also for the identification of selected discharges by fingerprints of combinations of different parameters. The other field of application is the forecast of hydrogen sulfate emissions in the sewage, and maybe as a perspective also the control of this type of emissions. And in a later stage, we will transfer the experiences of the other two applications to improve risk management concepts for water reuse, what is a topic of the future, we think. If you operate such an automatic monitoring system, you get data bundles like this. They are influenced, for example, you can see it by the time of the day or by weather conditions or by other effects, which are easily to see. But if you try to get more in detail, it's more or less not possible to identify specific patterns between all the parameters. Therefore, we currently try to minimize the number of the parameters to be measured to those that are really relevant, minimization. And on the other hand, and that's the main part of the project, to support the data analysis by AI algorithms. Here you can see the typical implemented training process of this AI-based analysis for the recognition of patterns. The process is completely digitalized, but we quickly had to realize that still the supervision by humans, by operational experts, is necessary for getting results with really, it's difficult here, for verified patterns which you can use later on for the automatic monitoring routines within the sewer network. There are some more lessons learned during the project times. I just picked up two of them. One is that it's very important to ensure to have synchronized measurement data, especially when we have sensors of different types for different parameters and at several measuring points. And the second one is to do everything digitally, even to document, for example, operational interventions like the maintenance of sensors, because only if it's digital, it's possible to process them by the algorithms. By doing this, we are confident that we will develop a useful monitoring system, which opens up several interesting opens for further applications. So, thank you very much so far, and I'm looking forward to your questions.
Thank you very much. So keep your questions for the end of the session. We will have a discussion then. Thank you very much. Next up is Dr. Daniel Klein from Lippeverband, and he's going to present the project SoftSense.
Yeah, thank you very much for the introduction. Coming from the wastewater before the wastewater treatment process to the end of the wastewater treatment process, which is sewage sludge, different sludges on wastewater treatment plants. And we want to assess in our project the quality of sewage sludges via a soft sensor approach. Oops. Just a short reminder, we are implementing the soft sensor in pumps because you have pumps everywhere on wastewater treatment plants. You have to pump the sludge, of course, you have to pump wastewater, you have to pump different other liquids. So it's the idea to use the data of the pump, like pressure, temperature, power consumption, to gain information about the properties of the fluid that is pumped. So just a short reminder and one example, the polymer solution. Polymers are needed on wastewater treatment plants for sludge dewatering. You need it on every wastewater treatment plant. So there is a wide approach or use cases all over Germany. So usually the polymer solution and the concentration of these polymers used for for sludge dewatering is not measured. You have like the polymers and you dilute it with water, and then you add it to the sludge for the dewatering. Usually this is not controlled, so our idea is one of the 3 points we use the soft sensor for an online measurement of these polymer solutions. This means have an online concentration of those polymer solutions during the operation. Before going on a real wastewater treatment plant, we are testing the soft sensor in laboratory. So our project partner CPEX has a laboratory pump where everything can be done under lab scale conditions. This means you can add a different, you can add like a specific liquid in the pump. You see the pump here. You have all the data evaluation. Before using this system for real sludges and real wastewater, it is used with like artificial substances like water with bentonite to as a sewage sludge, and water with polyethylene glycol to simulate the polymer solutions. And having this data in lab, all the pump parameters are assessed in lab scale. So we have different pressure sensors on the pump. We have the data from the electricity and the power consumption. We have temperature sensors, and all this data is assessed in lab scale before we go with this idea on full scale on wastewater treatment plants. And of course, all this data has to go into mathematical models. And to explain what happens on the mathematical side, I will give over to Julian from the University of Bochum for the next few slides.
Yes, and on this slide I try to sum up what the physical properties of the used pump are and what the aim is that we desire. So basically what we have is a pump, and we try to model this pump in a pretty simple way, basically, just to have a digital twin, to come back to Mr. Olber. This is our understanding of a digital twin, basically to have a mathematical model that takes input parameters or input states and produce some outputs. In this case, it is the tilt of the rotor, basically the dynamic behavior of the rotor itself. And as you can see, we have some dynamics that we can measure. For example, the torque dynamics with the frequency inverter data. And this is basically what happens inside the pump. We try to put this into a model, basically, on the mathematical approach. using this kind of relationship. And what we try to do is that we try to select the number of states sufficiently small to guarantee real-time feasibility, to have a so-called observer to estimate the total solids on a real-time basis. Because it's always hard to model this kind of systems, we also create a data-based model, basically to, coming back again to Ms. Teuber, have a hybrid digital twin to catch all dynamics that occur in the real plant. All right, that's it with SoftSense. And if somebody has questions, I prepared a poster, and maybe just come back to us.
Thank you. So maybe you Okay, thank you very much. Next up is Professor Dr. Andrea Comignola presenting the project YOLO.
Thanks a lot, Dr. Teuber. All right, so we move a little bit more upstream now from wastewater to drinking water, in fact, and we talk about the YOLO project with an emphasis on the UX/UI component that we're developing. And leakage detection is actually a problem that has been there, I would say, forever. It's been there for a long time, so it must be solved. In fact, it's not, and in order to explain why it's not, and because I'm originally Italian, I need to talk about pizza. So I'm gonna steal an example from David Staffelbauer, our colleague at KWB, that always says, imagine you order a pizza, and once it gets to your house, on the way from the restaurant to your house, a quarter of it was eaten by the pizza guy. You would not be happy. Well, this is what happens with water on average in Europe, so it's not definitely a solved problem. 1/4 of the water that is supplied in the network is lost on the way to its customers. If we look at the numbers worldwide in terms of water that's lost, billions of cubic meters, and related costs, no revenue water, then the numbers are really alarming. And we saw there's a gap. Solutions exist, of course. The problem has been there for a long time. Solutions have been developed, but there's a gap between what happens in practice with a lot of inertia, sensors-based solution, water audits, and what can be done a bit more automatically, which sometimes stays just in research, or maybe in case-specific applications. So we wondered what's needed in order to have a successful and robust solution for leakage detection and identification in water distribution networks. In our project, we basically try to give an answer to this by saying that a solution should be integrated, robust, and human-centered. So let's open the 3 boxes that we have here, and I'll showcase what we've done in the last year and what we're actually working on at the moment. For more details, if there's no time now, there's of course questions, and we have a poster later, which I invite you to attend. Let's start from integrated. In our platform, digital platform for leakage detection, we integrate 2 state-of-the-art models. We've been further developing them in the last 1 year, one developed by us at TU Berlin, the other one at KWB. And the 2 models have a really strong difference in the philosophy and the rationale, but at the end of the day, they aim to provide similar outputs. They aim to identify when a leakage is occurring, and in one of the 2 cases more than the other, where the leakage is occurring. So they reply to different requirements and needs by water utility. Altogether, probably, they can contribute to a more robust and accurate solution than just one of the 2 options. Robust. We want algorithms that work under different circumstances. So we've made an effort to classify all factors that could affect the performance of our algorithm. We classify them in aleatoric uncertainties, which are a bit more outside of our control, its leakage scenario and the type of network or the system inputs, and epistemic uncertainties, which are factors that at least the water utility, maybe with a longer term, can also control, like measurement, quality of measurement data, hydraulic parameters, and also then the parameters of our algorithms. And we are tackling the effects of these, we are assessing the effect of all these factors on our algorithms with a global sensitivity analysis so that we can provide utilities with actual insights on where they could change things in such a way that the resulting leakage detection is more accurate and trustworthy. Finally, and for this presentation, probably also the point that I wanted to highlight, because that's where we're investing a lot of our effort, is really making this solution usable to water utilities. We started in the first year of the project with a market search, so we organized basically a structured analysis. We performed a structured analysis of which players are in the market. The leakage detection is actually a very active market. We saw actually 45 relevant startups, most of them software-based, many of them claiming or stating they use AI in different ways, and also relevant utilities that may be interested in engaging. In what we are planning now, we have already started interacting with some of them, where we're really seeking for their input, stakeholder engagement. We don't want to just develop the next leakage detection solution. We want to develop the next leakage detection solution which they can use, which they like, which they feel comfortable with. So we started actually with a mock-up of the user interface based on also on some feedback and interactions we had early on with some water utilities. We're now pushing this to the next level, where we start really a round of feedback with water utilities to really have it displayed, not really what we want, but what they think is useful for the actual application. So I guess with this, I would like to also thank the partners of the project, KBB and Urban Impact Agency and Gemeinsam. And for more questions, I'm happy to answer later. And Deposa.
Thank you, Andrea. So, yeah, next up, Dr. Ulf Mier from Konferenztagen Wasser, presenting Digital Wave.
Yeah, thanks for the introduction. So now, to confuse all the non-water expert completely, we are back now for water reuse. So we're at the end of the wastewater treatment plant. So what's happening after we have treated the water? So our project is about using predictive models for efficient water reuse for urban areas. So let's see, which one is this? Maybe this one. Ah, this one. So, background. I think all of us like urban green, have nice trees, which gives us shade, especially in hot summertime. But it also turned out in the last years that these very long water scarce periods, a lot of heat, gave a lot of pressure to basically the management of urban green and increase also the water demand. And the question is also, okay, can we replace this water demand for irrigation by another source instead of using either groundwater or surface water, even maybe drinking water, by doing water reuse? And this is a core focus, and we want to support municipalities by using digital tools during the planning, but also during the operation of water reuse. So, oh, no, that's the wrong direction. Ah, this one. So, we have several elements here. One is about a prediction tool for the microbial water quality, upfront to UV disinfection. Then the question is like, how much water is needed, where in the city area? And then also a question like, okay, when we would have to deliver the water in the city, it's about route planning of water trucks, or maybe even if we would have a pipeline, where to put, basically where to extract the water from the pipe to reduce the demand for long distance transport within the city. So basically it's all about reducing the effort for those managing the urban green. So, data acquisition. First, let's have a look on the microbial water quality prediction. This is existing in full scale. So we have our wastewater treatment plant. It already has a dual media filter and an activated carbon filter to remove pharmaceuticals. And this is then where we start. Basically using, we installed a UV disinfection pilot plant. And then we take a lot of samples, like lab samples, but also a lot of online sampling, basically from the wastewater treatment plant, from the treatment processes. Here you can see, for example, of course, we need factors like turbidity, UVA, all nice water quality parameters. We also installed let's call it the at-line E. coli monitoring. So each, let's say, 6 to 8 hours, we get also a value for E. coli to train our model. Yeah, and then of course some results. This is like more the classic water quality parameters you need for water reuse. So these are all fecal indicator organisms such as E. coli, enterococci, coliphages, or Clostridium perfringens for the different types of risks you have in water reuse. And what is now interesting for us is we want to predict the E. coli value before the UV disinfection, because at the end we want to make sure that the UV disinfection always reaches a value below 10 E. coli per 100 milliliters, while we are starting, well, in the entry by more than 10 to the power 6. And this is like where one of the models is targeting at, and this model is taking, of course, into account different factors like the flow in the wastewater treatment plant, the turbidity in the effluent, temperature, but also conductivity of the water. And this is then modeled, and we use especially this online device here to get a lot of data as a training data set. Using a random forest model to train this, but also to check against actual lab data. So this is then important to have this lab data, and here you can see the, oh, this was the wrong direction. So here you can see, this is quite sensitive, huh? And here, for example, you can see now the correlation between the actual measured E. coli values and the predicted ones. So for microbial data, this is excellent. So keep in mind, this is microbial data with a lot of scattering. And then below you see basically the prediction against measured E. coli values which are not part of the training data set. Of course, here the correlation is a little less good, but still for microbial there is quite well correlation. Well, that's basically where we are, and now the next step is, of course, now to make the next step to say, like, how much energy we do need for the UV disinfection. One slide more I have. This is one part we are still working on. Here we have it's more challenging, because here it's about what we want to do is to basically predict the water demand in the area. And currently the state of art would be to measure the soil moisture. So this is what you can buy on the market, but this requires that you put a lot of sensors in the city area. And the idea is to use mostly open available data, for example, by the German Weather Service, to predict the soil moisture. And this is work still ongoing, but just to give you a bit like, so this is the actual measured soil moisture, so it's not the actual value, but changes in soil moisture. And here you see where we are currently with the modeling. You can, for example, see some of the peaks are fitting quite well. There are some peaks which may are fitting not so well, so it's still ongoing work. Yeah, this is then used to really help the public utility with the management of urban green, but and next year, of course, we need to go then to our test phase during the actual irrigation phase. So we still have a lot of work to be done until, let's say, April. So, and that's everything from my side. Thank you.
Thank you very much. So, next up would be, right, agents for two water markets. Mr. Glück and Ms. Henn, please.
Thank you for the introduction. With Agents for Two Water Markets, we are again back at the drinking water, and as the name of the project already suggests we are looking at water markets and agents, and down at the bottom you see the first water market where we look at water consumers and water supplier, and we both consider them as agents in our project. And the second water market we are looking at is the cyber-physical water market, where we look at the technical system of a water distribution network. And here all components like pumps and valves are connected to agents or represented by agents. And with the project, we want to establish a path to future water infrastructure, which from our perspective needs to be, it's really laggy, sustainable, resilient, and fair. And in the following, Mr. Glück and I will explain how we address these obstacles in the project. So first, let's start with resilience. What we're seeing here is a really simple water network consisting of pumps and valves. And basically, at the moment, there are two operation strategies for such a system. Either there is the centralized option where all components are connected to one controller, meaning the system can be operated quite energy efficiently, but it requires a lot of effort during setup. On the other hand, you can operate such a system with local controllers, which is really basic and less energy efficient. And with Agents for Water Markets, we are combining the benefits of both these strategies in agent-based control, where each component, so every pump and valve, is connected to an agent, and via communication between these agents, we can ensure cooperation. And when an agent is now able to anticipate, monitor, react, and learn from such a system, we can ensure that the operation can be resilient. And in practice, we are investigating such systems at a test rig, and here the agent is mainly based on a microcontroller, and for example, we are testing different communication protocols for these agents. And Mr. Glück is continuing with sustainability and fairness.
Yes, thank you, Katharina. So another key aspect we are focusing on is sustainability. And in order to control a hydraulic system sustainable, we need to be efficient. And today in the keynote at the beginning, we heard that efficiency is not enough. We also need to be sufficient. So the key here is to supply only as much as there's really need for. And also the control system as such to be sustainable, it is necessary that it's adaptive, since the environment is constantly changing. And how are we going to do this? We have introduced an environment where each agent can trade and negotiate with each other and find autonomously the most beneficial solution for the complete system. And for this method, it is necessary that all these negotiations are transparent and fair. So we are also investigating different pricing schemes to allocate the resource effectively and efficiently. Efficient. Thanks. We are here have some categories, for example, that will be fed into the agent-based model, on which we can try to make the allocation fair. So if this sparked your interest, you are invited to our poster and ask your questions. Thanks.
So thank you very much. I hope it's okay if I keep you up here a little longer. So everyone who just presented their projects, please come up. We want to have a little discussion, clarify some questions. And to the audience, you can already think of all the presenters. Do you have any questions? Any open questions left? Do we have another microphone? Yeah, in the back, right? Yeah, okay, perfect. So are there any questions? Not too many. Please. Okay. Yeah. So I might have one. Oh, there's one. Thank you. It's coming.
Yes, I have one question for the last presenters, actually. It was very interesting. But could you provide an example what the different agents learn and how they cooperate and which decisions they, for example, support or make?
At the moment, we are not so much focusing on reinforcement learning, so not so much on learning. We are more inspired from game theory and market design, but just a side note. Currently, we are looking at simple water networks, which are basically circular, and we are assuming we have speed-controlled pump where we can change rotational speed depending on the load case, and we try finding an optimal set point for these pumps with really easy to understand rules, so avoiding a black box model. That's what we are at. Is that answering the question?
Yeah.
Okay, any other questions? Yeah, in the back.
Are there already any maybe projects or just opportunities to exchange about synergies across the projects?
So, does anyone want to say anything about this? I know there are some working groups, right?
Dann nehme ich das. Yeah, I mean, I'm not sure how much I was in the other workshop, so I think there's also a lot of what I'm curious to see between projects, especially I'm more, of course, bound to these water projects, how this factor of explainable AI is going in at the end. Can we really make decisions transparent? Because I think, especially in the public sector, it would be nice also to know, okay, on what kind of models and how we come to a certain decision. I think that's an important connecting point between all these projects. And I personally, I think there's also an aspect on water reuse, like risk management. So that's something I would be interested in.
Maybe I'd like to add on this, Ulf, because I think explainability is definitely a key factor, particularly for those solutions that have AI, maybe. But also in general, I think broadly speaking, for also the other solutions, an aspect for discussion would be the usability in general, which can go hand in hand together with explainability, because if you understand something, maybe you trust that thing a bit more and then you're more prone to use it, but there's also other features. So like we use this human-centered code design. So I think discussion like these topics would really foster joint discussion across different projects.
Yeah, what I like is especially the fact that consider the fact that sometimes you read a paper and you see some cool approaches that someone did in China, for example, or so. But basically, we all have equal problems, not the same, but kindly the same. And I really like the fact that on this basis, for example, we can exchange and elaborate problems that occurred in our projects.
Thank you. So, any other questions? So, maybe I would have one. So, there is the EU AI Act coming up, and it also contains directives for training personnel that uses AI. So how is this affecting your project work currently? Are there thoughts about this?
Maybe I can take a first start, I guess, also to break the ice a little. So we don't have really a strong AI concept in our project, in the sense that our solution, in order to be usable by the relevant stakeholders, water utilities in this case, is really grounded on physical knowledge. Then we have tried also, we might still keep some small AI to correlate better data and so on. But in general, I think, despite this fact, I think the point that you're raising is very much important, because one aspect is what's contained in the regulation, in the guidelines, in the law. One aspect is really about the training. So I think regardless whether there's AI or not, it's interesting to have some sort of training in this project in order to make the solutions then really transferable from what we do in research to the practice. So of course we have the partners already involved. Ideally we would like maybe a solution not to be adopted by just one partner, but also by other similar stakeholders. So some sort of trainings, I think, is very fundamental. For instance, in our project, we are doing different types of, we're organizing different types of interactions in Jole. Even before the training, we really just start from the requirements. So in the last 1 year, we also had one-on-one interactions with water utilities to understand what their bottleneck or why they stick to the solution they currently have in place is, whether they trust the solution they have, what could be the risks and uncertainties related to that. And I think this is then the first step. Once one understands that, I think then the training, of course, comes more once you have the solution ready, basically. But I wanted to emphasize what comes first, so the requirements and the co-design in the between, and that's something we're, at least for Jole, we're investing quite a bit. So.
For example, in our case, it's more, I don't like this buzzing AI words in my case. I think it's more like training, for example, small machine learning models to sufficiently be able to solve your problem. And as in the previous talk, somebody already mentioned, going back to smaller models and smaller data sets, and often then you don't have those problems. For example, how to be safe, how to ensure IT security, because you run your model on an embedded system, for example. Be small and energy efficient, and often this already solves your case using not complicated neural networks, but linear regression, or least squares or something like that. And this is often better than using those neural networks, highly complicated algorithms, and then you don't have, often you don't have those problems with regulations.
Yeah, thank you very much. One last question. We had this in the game 2045 or 2035. What is your hope for the future for your projects? What needs to happen for them? What do you wish them for to happen in the future? And where will they be in 2045? Doesn't mean.
Yeah, maybe I can answer. As I already mentioned, we have some applications in our view, and so we hope that these applications will become reality in 10 years.
Okay, probably I can add. The same for us. We have specific applications for our SoftSense project. And of course, these applications are real. So we have these applications on almost every wastewater treatment plant. So there is a large potential to really implement those systems. And of course, I hope, and I really think so, that we will have kind of soft sensors in the future. But I can add to that what Julian said. It will depend. Will it be a very complex, let's say, AI approach, or will it just be improved data, improved knowledge to have an improved control of our wastewater treatment plants? So there is probably a wide range of just knowing more up to complex, let's say, controlling models, but there will be something in between that improves the operation of our wastewater treatment plants, of course.
I guess for us, probably a couple of quick things. One is definitely to get almost the entire pizza back, since I mentioned the example, so to reduce the leakages. But in general, I think also what I would wish more on that specific problem and development of solution is, on the one hand, flexibility of solutions, so to really overcome these specific solutions for only some cases, because then transferability takes always a lot of time and the benefit could be great. And second, really reconcile these two worlds that sometimes are still a bit far of research and practice in this particular problem.
Yeah, for us, I think it has two main factors, and one is not so much bound to the digital part of the project. It's more like that I would like to see water reuse, especially in urban areas, to be, let's say, a standard solution in 10 years. That maybe in Bad Oeynhausen we have a second pipeline in the city area used then for sport field irrigation, also for managing the public green. And now the digital part, that also we achieve that such tools like prediction tools, real-time monitoring, become an integral part of the risk management. Because at the end it's risk management. We want to support the risk management, we want to support that the water is efficiently used in the city area, and that's basically what I hope for Bad Oeynhausen, maybe in 5 years.
Thank you.
Yeah, specifically for our project, I see still a technical risk for the agents because of the communication. It's a distributed network and we need the connectivity. So even with 5G and all the Internet of Things, I think, or I would be happy if this would still improve and make such solutions more viable. And another thing is those solutions, yeah, they must be made in a way that there's no real expert needed to operate them, since we don't have so many experts, I think, yeah.
Thank you very much. So that's it from my side. If there are no further questions, thank you very much for the nice talks. And I cannot clap, but I have two microphones.
I have one question to you, because I really like the question about symbiosis of these projects. I thought the same. That would be really great to connect some of the projects. Could you imagine that? I mean, they could, they answered, but a little bit, they hesitate a little bit.
Yeah, of course I have the yeah,
one is enough.
Yeah, for connected systems, but at the same time, I think they need to be sufficient. I agree with the previous keynote that we need to see what models do we really need, how much digitalization, because it comes with the cost, right? To see the training, the workforce training, and so on. Yeah.
Okay, so, and smaller models, as we heard,
I agree with the others.
Efficient enough. Okay,
definitely.
So thank you very much for your inspiring keynote, and the projects were presented here. So thank you very much for listening today. You have the opportunity to ask more questions at the poster session. It's in this room there. There's also food. Probably you're hungry after the long day. And tomorrow at the conference we will present the Digital Green Talents Award and 4 projects that are left. It's about using digitalization for more recycling and resource efficiency. So keep up, and you're welcome to be here tomorrow as well. And so, is there anything else I forgot? I don't know. I don't think so. So we have your food there and the poster sessions and more talk and more opportunity to network. Thank you for listening and asking questions, and hope to see you tomorrow.